experiment we are about to perform is called frequency calibration. It's like less of an experiment and more of a like rather knowing this particular instrument, which is called an oscilloscope, and this one over here is called a frequency generator. So our goal is to generate frequency from this frequency generator, and we will see that if we can get like if we can get same output from this oscilloscope. Okay, so as you can see, let me open this. So let me open this thing, and okay, so if I turn on this oscilloscope, this is power on, then you can see that there are two channels, channel 1 and channel 2. I have connected this cable to channel 2, and this cable will be used to take input from this frequency generator, and you can see that there is a positive terminal of this in this end, and a negative terminal. So okay, so as you can see, there is nothing except this blue line over here. So we will check if this thing is working or not. So I will stuck this positive terminal to this 2-volt square wave, and let's see, let me scale this. So let's see, we can we have generated this square wave, and we can say that our oscilloscope is working. And if we get back to this particular instrument, which is known as frequency generator, and if we turn this on, this dial over here shows the value of the frequency, and we can like increase or decrease our frequency using this knob. And as you can see that this is in like kilohertz range. We can change it to millihertz, megahertz, or even in hertz. And as you can see, there is like these buttons over here. We can use square wave, we can use triangular wave, or we can use sine wave. So now you can see the output of this frequency generator has two terminals as well. The red one is positive and the black one is negative. So from this circuit diagram, you can see that it's an like easy setup. We just have to connect the positive terminals and connect the negative terminals together. So let me, okay, this is kind of okay. So I have connected positive terminal of this frequency generator to the positive terminal of oscilloscope, and so the negative terminal same as well. And I will, so this is an digital oscilloscope. It has a button called auto set. If we keep this button, as you can see, we have got sine wave. We also can, if I push this button, it gives square wave, and if I push this triangular button, I get triangular wave. So I hope you know how to calculate the wavelength of a wave. So if I scale this, the wavelength should be from the top of this point to the top of this point. So and as you can see, my input is like around 15 hertz. So I will try to recover the 15 hertz from this graph. So let me scale this again and position this. Okay, all right. So as you can see, the time division is 10 millisecond, which means each square box here represents 10 millisecond. So I will calculate the distance between this point and this point. So that will be 1, 2, 3, 4, 5, 6 and 6 point something. how much? So this as you can see, there are like 5 small dots each. So the whole box represents 10 millisecond. So the small each small point should represents so the 5 box represents 10 milliseconds. So each small box should represents 2 millisecond. Okay. So we can say that the distance between these points are 5 sorry 10, 20, 30, 40, 50, 60 and 62. I am sorry so 64 millisecond. So as you know that frequency f is equals to 1 by t. So I can say the time division is 64 millisecond. So this is 64 into 10 inverse 3 and 1 divided by answer, which is our frequency, is equals to 15.625, which is almost same as 15.7. So we know how to calculate this thing. So now our goal will be give these frequencies over here 50, 100, 150 as input, and we will see if we can recover this from our oscilloscope. So as your table says, I will set this up to 50 hertz. Okay, let me choose a sensitive equipment. Okay, so now as you can see, this is 50 point something, and I will see if I can get 50 hertz from this oscilloscope. I need a close shot for this, so I hope. So in this case you have to trust me. The time per division is written over here, which is now 5 millisecond, as I have scaled this according to my convenience. And as you can see, let me position this perfectly. Okay, so now each small box represents 5 milliseconds. So the distance from this point to this point is 5, 10, 15, 20. Okay, so I can calculate. So now this is 20 millisecond. So this frequency will be so the frequency so the time period will now we can see that time period is 20 millisecond, which is equals to 20 times 10 inverse 3 second. This is 1 divided by 20 into 1000, which is equals to so as you can see, the frequency is equals to 1 by time period. So 1 divided by 20 into 10 inverse 10 to the power minus 3, which is equals to 50 hertz. So I have got exactly 50 hertz from this experiment. So let's change our frequency to, so let me change it to 100 and okay 104, 98, 99, okay 100, and let me scale this again according to my convenience. So okay, now once again you have to trust me. Now this time division over here is 2 millisecond, and so the distance from this point to this point is 2, 4, 8, 6, 2, 4, 6, 8, 10. So the time period is 10 millisecond, which is equals to 10 inverse 3. So basically 1 divided by 100, sorry, 10 into 10 inverse 3, and 1 divided by answer is equals to 100. So we have got 100 hertz. Let me do one more, and this is 150. Now the time division is same 2 millisecond, but let me position this. Okay, now now as you can see, this is 2, 4, 8, and as you can see there are like small dots in this square box. So the 5 dot represents 2 millisecond. So 1 dot should represents 2 by 5, and now so this is 5, 10, 15, 16, 17. So it should be 17 times 2.5, which is equals to 42.5 millisecond. 42.5 millisecond, which is equals to 42 times 10 inverse 3, now into 10 inverse 3, and 1 divided by answer. Okay, so okay, I must have done something wrong. Let me calculate this again. So this thing is like so. Let me scale this according to my okay. So as you can see, so each small boxes contains 5 small dots. So how many dots are there? 5, 10, 15, 17 dots. Okay, from this point to this point, and each small dot represents so each box represents 5 millisecond. So the 5 dot, sorry, 2 millisecond. So 5 dot represents 2 millisecond. So 1 dot represents 2 by 5 millisecond. So the distance from this point to this point contains 17 dots. So it must be 17 into 2 divided by 5, which is 6.8 millisecond. So this one should be 6.8 millisecond, which is equals to 6.8 times 10 inverse 3. So answer into 10 inverse 3. Okay, so 1 divided by answer should look like 147.0.58. So 147.0.058. So my input was 149.9, which is around 150, and I have got 147 point something. So I will do the experiment, continue the experiment with 250, 300, and let's see what happens. So I have done the experiment and filled this table up, and as you can see that from this particular input frequency we have got this output frequencies. Now your job is will be to plot these frequencies. So the signal generator frequency in x axis and the output from the oscilloscope in y axis, and you will calculate the slope. Ideally you should get 1, but you will calculate the slope and see the error in your experiment.